Hello everyone, we're Group 9 and today we're ready to present our research. These are our crew.
Hi, I'm Jiacheng.
Hi, I'm Reggie.
Hello everyone, this is Jason and today I'll be presenting literature review part in our report.
Hello, I'm Wei Yu Zhang.
Hi, I'm Helen from Group 9.
Hello, I'm Alex. Our presentation consists of the following parts. Firstly, I will introduce our topic and give some brief background information. Then we will go through the literature review, the data description, the pre-processed data. We will also explain initial explanatory analysis, the model we choose, and the co-integration test along with our results. And lastly, we will draw a conclusion of our project. Our topic is whether there is a long-run relationship among the primary energy contributors such as coal, crude oil, and natural gas, renewable energy, and the ASX 200 energy prices. Okay, now, why this topic is important? Australia possesses abundant unconventional energy sources. Australia is a net energy exporter and was the fourth highest coal producer in the world in 2009, producing 335 megatons of black coal and 64 megatons of brown coal. Additionally, Australia has about 0.3% of the world oil reserves. The natural gas is the third highest energy source in Australia. It is used by power stations for electricity generation, factories for manufacturing, and homes for heating and cooking. These energy sources play an important role in supporting Australia's domestic demand, powering its industries, and contributing significantly to the country's economic prosperity. However, the use of conventional energy sources can cause environmental issues such as greenhouse effect. Especially in recent years, as part of the Paris Agreement, more and more countries have started to transition to new energy sources in many industries, which has impacted the traditional energy market. So in order to quantify the traditional energy market, we choose the ASX 200 Energy Sectors Index as an indicator. This index is a market capitalization weighted and float adjustable stock index listed on the Australian Stock Exchange, representing 84% of the entire Australian stock market. Its energy component comprises 11 companies classified by the Global Industry Classification Standard. Now let's move on to the next part.
Moving on to the literature review part, I'll be discussing our choice of model for our research on the relationship between energy prices and stock market movements. Our first point of reference is the work of Gupta and Waha in 2017. They illustrated the effectiveness of VAR models. They emphasize the causal relationship between oil prices and the stock prices, suggesting that VAR has a significant benefits when dealing with a two-way relationship. This is further validated by the work of Suhasona and colleagues in 2017, who demonstrated the effectiveness of the VAR model in analyzing the relationship between variables in the study of the ASEA and stock price index. On the other hand, other models such as like ARIMA model were found to be ineffective and unreliable, as shown by Mallikarjunan and Rao in 2019. Based on these advantageous features, we have determined that VAR model is preferable for our research topic. Moving on to the selection of variables for our model, we turn to the work of Hassan in 2017. His results demonstrate the strong correlation between the oil, natural gas, and the ASX energy sectors, emphasizing the necessity of including these variables in our model. In addition, Tutek and Brodny in 2022 found that the rise of renewable energy could impact the conventional energy market. Finally, Obendofa in 2009 concluded that the oil had a greater impact on European energy sectors than other energy-related commodities. This raises consideration for our study, especially whether other energy commodities will have a long-term relationship with the price of Australian energy stocks. In conclusion, it is essential for us to investigate the relationship between stock prices and both renewable energy and the conventional energy prices simultaneously in our model.
In this section, we will provide a description on our variables and how we perform data cleaning to make sure the samples are ready for our further study. The ASX 200 energy sector refers to an index that contains 10 companies' stocks focusing on exploration, refining, marketing, storage, transportation, equipment, and services of oil, gas, and coal. We treat the closing price of this index as our dependent variable and study the different relationship between it and our other variables. The index experienced exponential increase from March 2003 to the beginning of 2011 and suffered steep falls in 3 periods as labeled red arrows in the table. The crude oil price is the average spot price of Brent, Dubai, and WTI with same weight and converts to Australian dollar. Since there are 3 primary benchmarks, These are three primary benchmarks of the crude oil market. It makes our samples more standard and reliable. The crude oil price experienced three sharp falls and three booms. According to our studies, the main drivers of the shocks include decision of production made by OPEC, wars between countries, global pandemic, etc. The whole movement of crude oil has similar shocks compared to the graph of ASX 200 energy sector. This makes us curious if there is a long-term co-integration between crude oil and ASX 200 energy sector. The natural gas price was a spot price at Henry Hub and converted to Australian dollar. Henry Hub normal natural gas was also known as the pricing point for natural gas future contracts widely traded in exchange sites. The natural gas experienced three spurt in price as labeled by green arrows, and all of these growths were followed by a sharp price correction. According to our research, due to the scarcity of supply resulted from Ukraine war, the gas price sharply increased from 2022 Q1 from the graph. We found the natural gas also followed similar movement compared to the ASX 200 energy. This also makes us wonder if there exists long-term co-integration between these two variables, and we will prove it in our later study. The coal price variable refers to the price index for Australian thermal coal. The coal price trend was relatively stable until Q2 of 2021. The price sharply rose due to global excess demand. It fell from Q3 2022. According to research, the biggest threat of the Australian coal industry is the withdrawal of local Australian banks, that they followed the global trend to cut carbon emissions. To discover the long-term relationship might exist between renewable energy industry and conventional energy, we considered the closing price of three representative companies conducting lithium and tantalite mining. This includes Pilbara Minerals, Core Lithium, and Lake Resources. These three stock prices followed similar trend until Q1 of 2020, and all had a boom after Q1 of 2020. This was a result of global shortage of lithium, increasing demand of lithium batteries, and global environmental politics support. Then we conduct our data processing to make them suitable for our study. First, we selected the time frame of December 2003 to March of 2023 to conduct the investigation. We performed data feeding and data smoothing to cover the missing history price for all of these three stocks of renewable energy businesses, and we matched the time period we were interested in. These missing historic values are mostly caused by holidays and varied years of IPO. The development of energy storage for renewable energy was then regarded to be one of our variables by combining these three stocks into one index with the same weight. We then rescaled the ASX 200 energy price variable by dividing the data by 1000 to bring all the variables to a similar magnitude, so that our upcoming modeling procedure will not be impacted heavily. In the initial explanatory analysis section, we begin with carrying out the ADF test to determine if the time series of variables we've chosen are stationary or not. The null hypothesis indicates that the time series is non-stationary with unit root, while the alternative hypothesis indicates the opposite. We get the conclusion of failing in rejecting the null hypothesis since the p-value for four variables except coal price are all greater than 5% significance level, which indicates these four time series are not stationary. However, the price series for coal is stationary. By looking at the ACF plot, there exists a decay pattern indicating the presence of autocorrelation, such as the current value of the time series of ASX 200 energy price is highly correlated with its recent past values and becomes less correlated as the time lag increases. The PSAF plot tells there is a strong direct relationship between the current observation and the immediately preceding observation at lag 1, but no significant correlation between the observation after lag 1. Also, according to the graphs, there are no repeated patterns or notable spikes on the plot, which would indicate the data has no seasonality. To prove this, we simulated seasonal plot in R and visually see there's no seasonal peaks or seasonal trend exist. We then performed Canova-Hansen test, which further verified that there is no seasonality.
To capture the dynamic relationship, we firstly consider the ADL model, as it can include lag values of dependent variable, as well as the current and lag values of explanatory variables. Before running ADL regression, we want to understand how the lags affect. To identify the lag term should be used, instead of direct observing the ACF and PACF graph, we use the auto-ARIMA code to avoid the potential error from the impressionist of naked eye observation. The result we get is ARIM A000, and when we try to interpret this outcome, we first conjecture that it might be caused by the small amount of data. So we greatly increase our observations. But after that, the result is still the same. So we believe ADL model might be inappropriate for our study. Subsequently, we want to apply a vector autoregression model, which is a statistical model that can capture the relationship between multiple variables that change with time. Instead of clearly distinguishing independent and dependent variables, the VAR model only needs the variable include can be hypothesized to affect each other over time. Also, different from univariate autoregressive models, VAR model permit the bidirectional interactions between variables. The co-integration test we need to do later requires the data to be stationary after the first order difference. As we mentioned in the previous section, apart from the stationary call price, all other variables are first difference stationary. As the call price does not satisfy the condition, it is excluded when we performing this regression. Based on the AIC information criteria, a lag term of 3 is recommended. Therefore, our model with lag 3 is shown in the picture above, where Y is the ASX 200 index, oil is a crude oil price, gas is a natural gas price, and RES is the weighted renewable energy stock price. After running the regression, we conduct several tests to check whether our model satisfies some basic assumptions. Firstly, according to our test outcome, there exists no zero correlation, which is a good result. Secondly, as seen from the distribution below, although the residual is not normally distributed, it is a symmetric distribution with a mean zero, which can satisfy many properties of a normal distribution. So we do not think the non-smooth density and spec here are much of a problem in this regard. Finally, we detected the heteroscedasticity problem exists in our regression. So when choosing the co-integration test, we selected one method that should be least impacted by the heteroscedasticity. And this will be discussed further in the later section.
Finally, we have come to the section of co-integration tests. We'll start off by discussing 3 most commonly used types. Starting with Eagle-Granger test, introduced in 1987. It constructs errors based on static regression, and if the time series is co-integrated, then the errors will be essentially stationary, which can be verified using ADF test or other similar tests. However, there also exists a couple of issues regarding this approach. Firstly, in finite samples, unit root and co-integration tests have low power. Secondly, forced to asymmetrically treat the variables, designating one as dependent and the other one as independent. Finally, cannot conduct any hypothesis testing regarding the estimated co-integrating relationship. In the following, PO and John-Hansen tests are the modifications of Eagle-Granger co-integration tests based on its conceptual framework. The PO test is an improved version of Eagle-Granger test, which tackles some of its drawbacks, such as allowing multiple co-integrating relationships and takes into account potential endogeneity between variables, but more estimation steps and computational work is required. In addition, as we mentioned previously, by conducting ARCH and BP tests, there exists the problem of heteroscedasticity in our model. Given the existence of this problem, it was approved by past research that John-Hansen test performs a better and reliable result under heteroscedasticity, as well as addressing the issues associated with Eagle-Granger test. This brings us to choosing John-Hansen test as our final option for testing co-integration. Again, as previously pointed out, our time series variables are stationary in their first difference, that is, they are I1 series, but we would still conduct John-Hansen test on the level form rather than the first difference. The generic hypothesis test is as shown on the PowerPoint on the screen here. As you can see, the trace test statistics for the full hypothesis are shown on the right-hand side of the screen. From the output result generated by R, we are able to see both the test statistics and critical values at significance levels of 10%, 5%, and 1% respectively. Starting with the first hypothesis, R equals to 0, by looking at the output generated by R, the test statistics of 51.82 is greater than both critical values of 10% and 5%, but slightly lower than 1%, so that we have sufficient evidence to reject the null hypothesis of no co-integration equations. Moving on to the second hypothesis, the test value of 27.07 is lower than all critical values for all significance levels. As a result, we do not have sufficient evidence to reject the null hypothesis, so we can conclude the rank of the matrix R is not greater than 1. Therefore, the best estimation of the rank of the matrix is R equals to 1, suggesting that there's only one co-integrating vector, and we have a linear combination consists of only two variables to form a stationary time series. Additionally, we separately examined the co-integration between ASX 200 energy price and the price of natural gas, crude oil, and renewable energy. We discovered that the price of natural gas and the ASX 200 energy price are correlated because the test statistics of 18.08 is higher than both 10% and 5% significance level. We have sufficient information to reject the null hypothesis that there is no co-integration relationship. There is also sufficient evidence for deducing that there's only one co-integration equation, which is between ASX 200 energy price and natural gas price. So as you can see, our largest eigenvalue is approximately 0.1024. It corresponds to the vector given under the column YL3. From this output, we can form a linear combination of the co-integrated series using these vectors values. So as shown on the PowerPoint here, we could be able to receive a stationary series. This can be further verified by the plot of this stationary series and the result of the ADF tests, which shows there's no existence of a unit root. Lastly, we have come to the conclusion of ASX 200 energy price and natural gas price possess one long-term equilibrium relationship. This suggests that while two variables are not individually stationary, they may become stationary while combined. It implies further that these variables move together over time and are related over the long run. For extension, be mindful that the co-integration tests are incapable of demonstrating causality. They simply imply a long-term relationship, not causality.
Now I will illustrate three primary limitations of our model. There nevertheless remain limitations in terms of the reliability and accuracy of the results we obtained, despite the fact that our model and co-integration test successfully address our research topic. The first limitation is the probability of omitting important variables. Out of the 4 variables we chose, our co-integration test only found that one co-integration relationship between natural gas and ASX 200 energy, which might be insufficient. However, other numerous variables, such as economic indicators, may also have a significant effect on the ASX 200 energy index. The second limitation is the lag length. Longer lags may lead to identification of more co-integration relationships in Johansson's co-integration test. Therefore, the lag identification could have an impact on the outcome of our test. The third limitation is the insufficient sample size when heteroscedasticity exists. If the sample size is actually big, the Johansson test is the most reliable and will be the least influenced when there is heteroscedasticity. The sample size for our time series is 232, which will not be regarded as exceptionally abundant, leading to Johansson's test over-rejecting the null hypothesis. Therefore, in order to mitigate the detrimental effects of heteroscedasticity in the future advancement of co-integration test, we may consider expanding the sample size to eliminate this probability. To conclude, as the ASX 200 energy, the price of crude oil, natural gas, and renewable energy are non-stationary. Multiple problems such as a spurious regression could arise when implementing the conventional regression model to examine their long-term relationship. But based on our VAR regression and Johansson test outcomes, we found that the linear combination of ASX 200 energy and the natural gas prices is a stationary series. In other words, ASX 200 energy and natural gas prices move together over time by simplification, as there is a stable and equilibrium co-integration relationship between them. Thank you for your listening, and this is everything from Group 9.